At the beginning of time, there was nothing. Then everything sort of just came out of nowhere. In the video, The Big Bang Crash Course History #1, they explain,
in the barest fraction of the first second, the universe inflated from something many, many, many times smaller than an atom to about the size of a grapefruit. All of the antimatter created in the Big Bang had combined with matter and annihilated itself, leaving behind only 1/1000th of the matter created in the Big Bang. And that billionth is everything.
After this expansion went on for a while, there were elements everywhere, and lots of them.
Over time, gravity took hold, and this cloud of stardust collapsed into an enormous rotating disk, the solar nebula.
This quote was from the Origins video. Eventually, a big interstellar nebula, which is pretty much just a fancy word for a lot of elements circling a given point, was formed, and in the middle of it, our sun came to be. This nebula was full of gases, dust, rocks, and all kinds of elements. All of these things made everything in our solar system: planets, asteroids, etc. One way to help you understand how it worked is if 4 people took a scoop of snack mix out of the bowl, each cup with the scoop would have different percentages of each different snack randomly. That's what happened in the interstellar nebula, just a little different.
Gravity pulled, or scooped, the smaller objects around it towards it, causing them to combine. As they grew bigger, so did the gravitational pull, causing even more things to be pulled towards them. This eventually created our planet, as well as everything else in our galaxy.
This process is explained in the video Born Origins, Nova Neil deGrasse Tyson, when he explains,
dust grew into pebbles, and pebbles grew into rocks. And as the rocks grew larger, so did the collisions.
Because of the gravitational attraction between these bodies, you coalesce. Instead of just making a mess, and you do make a mess as well, you build bigger things because gravity holds things together.
In time, gravity shaped them into small, round planets.
As the Earth was being created, the heavier elements went to the middle of the Earth, while the lighter elements went to the top. Since the Earth was so hot, though, the Earth's surface was almost completely covered in lava, and the heavier elements, like iron, sunk to the middle of the Earth and melted into a lava ball of lava. This ball of lava was in constant motion, and because of that, it created some sort of force field around the Earth, shielding it from the majority of the deadly rays that could strip away the atmosphere. This lava center is also what causes compasses to point true north, through making some sort of magnetic pull. But since the lava is in constant motion, true north is slowly moving across the Earth and farther from the north.
Meanwhile, somewhere in the galaxy.
Greetings, humans.
No. You have to try it more alien-like,
Greetings, humans.
See, now try again.
Oh yeah, right, greetings, humans!
That's better. You have lots of time to practice your human greeting, because we went back in time to before the Earth had any life on it at all, and humans aren't going to be coming around for another few billion years.
And why did we come back that far again?
So we can see how Earth came to be what it is today.
I'm only here for the dinosaurs.
Well,
That will be a while. Oh, here we are.
Earth.
That doesn't look like Earth at all.
This is early Earth. The conditions are very different than the Earth that we are used to. Right now, the atmosphere is full of all kinds of gases coming from the lava, and most of that is steam and carbon dioxide. In fact, carbon dioxide is 95% of the Earth's atmosphere. Another difference is that early Earth was almost constantly in a barrage of meteors hitting it. Instead of rivers and seas, the Earth was covered in lava. There was no life at all.
Me God. Cool, I guess. I mean, it's not the best, but cool, I guess.
You guess? You guess? We are studying the creation of the Earth's atmosphere, how water came to Earth, and how life eventually came to be. And all you can say is that you guess that it's cool? It is more than cool. It is amazing. We are watching history happen. Isn't it at least a little exciting?
I guess it's interesting, me Flandy. I'm just wondering when something, I don't know, cool will happen, like, I don't know, dinosaurs or rainfall from the sky to create oceans or dinosaurs.
We will get there. Now watch this. See that meteor? Well, it's about to hit Earth and cause a part of the atmosphere to be taken away.
How does that happen?
I read this in a blue piece of paper called Caesar's Last Breath, and it reads, Asteroids. Motion got transformed into heat when it struck home. He was talking about Earth, you see.
I know.
Keep reading, or I'll just slap you with my tentacle. Wah!
Oh, sorry, well, he continues saying, heat that boiled atmospheric gases away into space. The rest of the kinetic energy created a gigantic shock wave that swept even more air up and away. Some geologists argue that impacts like these stripped our atmosphere.
Well, me Flandy, why is the atmosphere so important anyway?
Well, the atmosphere is what keeps out gases on Earth, as well as the heat.
Cool, I guess, me Flandy.
But wait! Where's the moon?
The moon?
Yes, the moon, me Flandy. What else would I be talking about?
Should be here somewhere. Wait! I remember something that I read in a yellow piece of paper, also called Caesar's Last Breath. It states, gravity, that eternal meddler, couldn't abide 2 planets circling in the same vicinity and within about 50 million years of their formation decided to bang them together like rocks. So that sounds like a Mars-sized planet is on the same line of orbit as the Earth was, and they run into each other at some point.
Like now, me friendly?
No, I don't think so. Why you ask?
Let it begin! Oh my gosh, that was awesome! You should have been there. Wait, you have.
It was not cool. We almost died. Cool is not the right word.
Wait, what's going on?
Oh, that's just the moon forming from all the many pieces of the old planet.
Then why isn't the moon the size of Mars then?
Oh, that's because some of the stuff combined with the Earth. This impact added a lot of water that Earth needed.
I don't see any water.
That's because it is all in the gaseous state.
What does that mean?
Goodness gracious, do you know anything? Everything can be turned into a solid, liquid, or gas. Gas is like the air. If you take heat from a gas, then it turns into a liquid. If you take heat from a liquid, then it turns into a solid. But if you add heat to a solid, then it turns into a liquid. And add heat to a liquid, it turns into a solid.
I read about this in a blue piece of paper called Caesar's Last Breath, where it states, every last substance in the periodic table can become a gas if hot enough. Then, later when it says, withdraw heat from a gas and it will do into a liquid, subtract more heat, and a solid forms.
So right now it's in a gas? And that means it won't turn into a liquid until Earth cooled down?
Correct.
But you said that a lot of the gas water came to Earth from the moon's impact. What causes the rest of the water to come?
This happened in many ways. First off, in the Blue Caesar's Last Breath paper, I read it said something about the magma or lava had dissolved lots of gases into it, like water, gold, etc., all in gas form. Like how sodas dissolve carbon into it. Well, from what we see now, it looks like a lot of this gas is trapped in the magma, started bubbling out. A lot of this got trapped within the earth and escaped through cracks, while others came through the holes of the volcanoes.
So that's cool. So it's like volcano soda.
Exactly like volcano soda. Do you remember that experiment we did a while ago with a carbohydrate and what happened to it?
Yeah, water was cooked out of it and started converting the jar.
Covering.
The jar in the water droplets and steam. And we learned that the water was trapped in a carbohydrate.
Carbohydrate.
And could be cooked out of it.
This was happening all over the place. Since it was so hot, water was being cooked out of all kinds of elements. But I saw in the Origins video that even with both of these things happening, there wouldn't be nearly enough water to fill up the oceans with.
What else could have brought the water to Earth, though?
Well, the video explained that the only other thing that could have brought water to Earth would have had to be the many asteroids and comets that constantly barraged Earth.
Space water!
Earth is in space.
Space water! Is the water in space?
Earth is in space!
Water is the water in... You know what? You're right. Wait a second. The Earth is tilted. How did that happen?
Oh, when the Mars moon ran into Earth, it caused it to tilt. Remember it said this in the Yellow Caesar's Last Breath paper, where it states, it also plowed deep into her mantle and left Earth lopsided. Which is one of the reasons that life eventually was able to form on Earth.
How did the moon causing it to tilt stabilize Earth?
It stabilized Earth because it caused there to be more than just summer and winter. It caused there to be seasons between to make the transition slower and safer for living creatures. I know this, where the paper later states, this impact gave us all sorts of poetic things, like full moons and even spring and autumn, since it nudged Earth sideways off its up and down axis and allowed for the variable sunlight that gives rise to seasons.
That's cool.
Look, the asteroids have almost stopped completely, and Earth is finally having time to cool down. Look, a new atmosphere is being created as we speak. All those volcanoes and cracks in the Earth are letting out tons of gases that will be kept to Earth because of gravity. This creates the atmosphere. I learned this, Johnny, from a website I found. The earliest atmosphere. Forces of Change, Smithsonian Institution. That's one name. Where it states, as Earth cooled, an atmosphere formed mainly from gases spewed from the volcanoes, included hydrogen, sulfide, methane, and 10 to 200 times as much carbon dioxide as today's atmosphere.
Okay, I get what the atmosphere does and how it was created and destroyed, but do creatures really need it, one, to survive, Sonny?
John, my slimy friend, the answer to that is yes. Because depending on the atmosphere, it determines other things that can determine whether or not life can survive. Like how hot the planet is, if water could survive in liquid form, how much pressure the planet has, how much sun rays will hit the surface, or other things of that sort. And you don't only need an atmosphere, but a good one. I learned about it in a TED Talk, What a Planet Needs to Sustain Life, where it says, you can't have too much atmosphere, too thick or too warm an atmosphere, because then you end up too hot like Venus. You can't have liquid water. But if you have too little an atmosphere and it's too thin and too cold, you end up like Mars, too cold. So Venus is too hot, Mars is too cold, and Earth is just right.
Oh, well now I know what life needs to survive. When are we going to see life?
Well, before any life happens, we need there to be water, and it is coming right now.
Finally, dinosaurs!
See, the Earth is cooling and clouds are forming because the atoms of the steam are slowing down and clumping together. And as it cools down more, it starts becoming more and more clumped, and then it starts the raining.
This is because when the heat is taken away from gas, it turns into liquid, right?
Correct. This is how the temperature had such a big impact on early Earth. It first was hot and got all the steam into the atmosphere. Then it cooled down and it started to turn the gas water into liquid form, which is one of the 3 Goldilocks conditions.
What are the Goldilocks conditions, Belle?
I'm glad you asked, John. There are 3 Goldilocks conditions: water, a source of energy, and finally, a source of food or nutrients. In a TED Talk, What a Planet Needs to Sustain Life, where it states that all life needs a source of energy, usually sun, but can also be from chemical reactions. There's many different energy sources on each planet. It also states that all things need a source of food or nourishment. 6 different chemical reactions that cause nutrients, all of which are on planets in our solar systems. Then it says that the last one is liquid water, which is very hard to find.
Wait, why is water acting weird?
Oh, that is just something humans call tides. It's caused by the moon pulling on the water, because though it has a weaker pull than Earth, it still has a strong enough gravitational pull to raise the water.
Why is it hot on the opposite side, too?
This is what happens. The moon pulls all the water close to it towards it, including the water on the sides of the Earth, or at least a lot of it. Then all the extra water goes to the opposite side of the Earth, because the moon can't pull. This causes there to be high tides on the same and opposite side of the moon. I learned this while doing a fun online simulation called Gizmo Tides.
Cool. Wait, what are those things in the water?
Those, my crazily excellent eye-sighted friend, are one-celled organisms that are called extremophiles. They produce oxygen. I learned from a video that is called Video Lays Out Earth's History on a Football Field, NPR, when it says single-celled organisms started to create oxygen. These tiny creatures live in the oceans and other water-covered places. I know this from the same video where he states, we're talking simple single cells floating in a vast ocean.
How did they create oxygen?
During the day, the planet would collect carbon dioxide from the air, and with the sunlight, it takes the carbon out of the carbon dioxide and turns it into sugar for energy and growth. It releases the oxygen into the atmosphere. I got this evidence from the Earth's atmosphere, PBS Learning Media, when it explained the process of photosynthesis.
Why is life coming just now and not earlier? What has changed that has caused these?
Before, when there were meteors and lava everywhere, there was no water and not really that good of an atmosphere to sustain life.
And before, you mean like 3 minutes ago?
Yeah, but in real life, it's more like a few billion years. It's just we don't have that much time for our video, and we have to speed it up.
Okay, continue.
But now there is water, a good temperature, and an atmosphere, so the one-celled organisms can survive.
How are these new organisms going to change how the atmosphere is?
Well, it's going to completely change the gas levels. It first had 95% carbon dioxide, and everything else was the last 5%. But slowly and steadily, the one-celled organisms started producing more and more oxygen, and the CO2 started to disappear. Once land plants start to arrive, though, the CO2 decreases crazily and almost completely disappears. Present-day Earth has less than 1% of CO2 left. I got this information from 2 graphs online. One was on the website Early and Changing Atmosphere, Excel 9 through 1 by chemistry teacher 001. And the other is from the website Composition, Uses of Gases in Air, experiment to determine the percent of oxygen in air.
That's crazy! What were the other percentages?
The specific percentages for early Earth are 95%, carbon dioxide 5%, everything else. Well, now the atmospheric gases have changed dramatically, with nitrogen making up 78% of the atmosphere and oxygen making up 21%. The last 1% contains the rest of the gases: steam, CO2, helium, etc. This information was found on the same 2 websites where they have graphs and such to show me.
Wait, is Earth normal now?
Yep, Earth is back to normal. See, now there are almost no active volcanoes, no meteors attacking surface, and life is thriving. See, there are little cities down there. Now you can try out your human greeting.
Yeah! Wait, We didn't see the dinosaurs.